Um, Hello, everyone. Good afternoon. Welcome to this session of DVCon. This is Formal Verification 1. I'm the session chair for this session. My name is Mitchell Poplinger. Formal verification is my favorite topic of all verification aspects, and I'm very passionate about formal. I just wish my management would also be more open to formal. It is my great honor to introduce and to moderate this session. We have 4 great paper presentations. These are all pre-recorded, like every other session on the DVCon this year. During the presentation, please type or post if you have questions in the chat box. After the presentation, we will have the presenters answer these questions live. And I want to remind everyone at the end to submit your ratings for best paper presentation. There is a voting button and you can submit at the end. Without further ado, let's have the first presentation. The paper is titled Accelerating Error Handling Verification of Complex Systems, a Formal Approach. We have 2 presenters. Bhushan Parikh is a senior architect at Intel Corporation, focusing on the development of various network accelerators from the quality and validation perspective. He is also a formal verification lead and coaches his team in this field. Bhushan has 10 years of industry experience in ASIC and SoC design verification, validation, and holds MS in electrical engineering, with an emphasis on VLSI and mixed signal circuit design from Arizona State University. Bhushan's technology interests include advancements in network accelerator, edge networking, formal verification, and machine learning. His non-technical interests include listening to music and travel. In his free time, Bhushan likes to play tabla, Indian hand drum, and watch and play cricket and basketball. The second presenter for this paper is Peter Graniello, also from Intel. He is a senior digital design engineer in Intel's Optane group, working on persistent memory design for Intel's Xeon-based data centers. His area of expertise is high-speed DDR5s, memory controller, and lossless decompression hardware accelerators. While doing decompression hardware accelerator, he was introduced to the world of formal property verification and has adopted this as a must-have validation method moving forward. He is currently the FPV lead for IOG and is exploring more areas of the memory controller design where engineers can adopt and implement FPV to help improve pre-silicon and post-silicon quality. In his spare time, Peter enjoys spending time with his wife and 3 young kids in the Arizona sun. As a former college football player for the University of Arizona, he still loves watching and following the game of football, as well as coaching and helping his children's sports team. Let's now watch the pre-recorded presentation.
Hello everyone. Welcome to the presentation of our paper, Accelerating Error Handling Verification of Complex Systems, a Formal Approach. In this presentation, we are going to talk about how formal verification can accelerate the task of error handling verification. Before I get started, I would like to thank my colleagues and co-authors Peter Graniello and Neha Rajendra for their contribution in the paper and the presentation. I will start the presentation with acronyms and their description for some of the terms that we will be using throughout the presentation. Then I will move on to the introduction section, which will describe importance of the error handling verification and the challenges associated with constraint-based random verification methodology. From there, my colleague Peter will talk about different FPV capabilities addressing these challenges along with examples. He will also go over results that shows clear impact of leveraging FPV and will wrap up with the summary. Here are some terms such as formal property verification, constraint-based random verification, which is also known as dynamic simulation-based verification, counterexample, and finite state machine, for which we will be using respective acronyms throughout the presentation. With this, let's get into the introduction section and understand the error handling verification. Error handling verification is the process comprised of anticipation, detection, and resolution of errors. It is one of the key components in evaluating reliability of the system. A reliable system ensures that it has correctly identified and reported the error. In addition, it guarantees that the system gracefully completes execution and stays available for the servicing the next task, thus maintaining the normal flow of execution. Now, the task of signing off error handling verification is equally challenging. Computer systems have achieved significant progress in the areas of technology, performance, and capability during the last quarter century. These systems are now distributed systems instead of a standalone system. Due to this, there are vast possibilities that can result in an error which the system needs to report, handle, and if possible, correct. This makes error handling verification extremely difficult to plan, execute, and deliver. Let's look at the classification of errors in the system to get more insight into this. The system errors can be classified into two main categories: undetectable and detectable. Since only detectable errors can be reported, handled, and corrected, handling of these errors falls in the scope of error handling verification. Now, detectable errors are further classified into two categories: hard errors, the errors due to which system cannot be used, for an example, non-repairable cell in the memory, and soft errors, the errors that impact only specific usage of the system. Soft errors can be further divided in three categories: memory errors, for an example, single bit errors in memory cells due to external energy radiation; specification violation errors, the errors due to violation of the specification; and lastly, the programming errors, the errors due to incorrect programming of the system. Coming to a complex system, we will use a lossless hardware decompression IP as an example of a complex system. A lossless hardware decompression IP consumes compressed data stream and produces uncompressed data, an idle signal indicating the process is complete, and error signals to reflect errors detected while processing. A compressed data stream consists of various multiple fields for defining the functionality. It is important to note that for a targeted compression algorithm, only some of the values and combination of these fields are valid. Also, these valid combinations are usually much less than the total possible combinations, leaving large set of combinations invalid. Now, reliability requirements of such lossless hardware decompression IP are to identify any invalid values or combinations of these fields as a spec error, report any detectable errors with the correct error code, complete the processing of erroneous use case gracefully. A high-level verification plan to address these requirements is comprised of error detection verification, that is, verify that detectable errors are detected correctly; error reporting verification, that is, verify that detected errors are reported with correct error code; and lastly, graceful completion verification, that is, verify that the system gracefully completed processing of any input data, including erroneous data stream as well. So now let's understand challenges associated with constraint-based random verification methodology. In constraint-based random verification methodology, software compressors are used to generate compressed data stream. Now, these software compressors are spec compliant and will not generate compressed streams with the spec error. Also, the assertion of an error is an asynchronous event with respect to the rest of the functionality. Due to this, the number of test cases can grow exponentially. Lastly, CBRV process is more manual and time-consuming, as verification engineer must identify each case and develop targeted test cases. Formal property verification methodology, or the FPV methodology, is widely accepted and commonly used methodology to achieve functional verification goals for non-error use case. However, what we found that it can be very effective in exposing bugs related to the error handling use cases as well. In the remaining presentation, my colleague Peter will share more information on various FPV capabilities which we found productive in addressing the challenges associated with CBRV methodology. With that, thank you very much. Handing over to you, Peter.
Thank you very much, Bhushan, for the great introduction on error handling verification requirements and challenges. The first technique is the ability for primary inputs of the design to be treated as free nets. This means inputs can be driven to every possible unconstrained value by the formal engines. Therefore, the engineer only needs to specify the expected behavior within an assertion, and the formal engine will create the correct stimulus to meet these requirements. This method gives the capability to hit multiple combinations for a given error within a single or small set of assertions to check for the correct detection and reporting. The table shown here gives an example of the specification requirements for block type and compression levels. For a given block type, only certain compression levels are valid, and all other values would be considered a spec violation. For block type 8, only compression levels of 1 through 20 are allowed in the block header, whereas type B only supports 1 through 9. Any other decoded value for either block type would be considered a spec violation. Since there are multiple block types with different requirements, we must check different combinations of compression levels. Thus, if checking whether the block type and compression levels from the header multi-bit fields is valid, with the right assertions, the formal tools will generate every possible combination of these multi-bit fields from the random compressed input stream to determine if the correct error asserts upon decoding a bad header input. In traditional constraint-based random verification, 12 different compressed payloads and tests for block type A and 23 different compressed payloads and tests for block type B are required to check all possible combinations of block type versus compression level. In the case of error handling, we want to see very specific behavior around the error conditions. Thus, it requires minimal design constraints to be put in place. Due to the under-constrained environment and specific behavior, counterexamples most likely translate to actual bugs. Let's take a look at a more detailed example of error detection verification using inputs as free nets. In this example, we want to verify that the compressed stream is not violating the block size specification. There are 3 block size characteristics that will be used to determine the correctness of the block size. Block max size indicates the maximum possible value of the field, but not necessarily the maximum possible value per the specification. Spec block size indicates the maximum value supported by the specification. And lastly, block size is the actual decoded value from the compressed stream header. In order to verify the error detection logic with full coverage, we need to check every possible combination of block max size. In CBRV, this results in multiple directed test vectors equating to block max size minus spec block size, just for the error detection correctness. This number of tests still does not fully cover the negative testing for this particular error. In FPV, using inputs as unconstrained free nets, only 2 assertions are needed to get full coverage. With these assertions, the formal engines will randomize every combination of the block size from the compressed payload. In addition, with FPV, we can achieve full negative testing to ensure that any combination of block size less than or equal to spec block size will never generate an error. While this example uses a straightforward error, the key takeaway is the ability for FPV to achieve full coverage with minimal effort versus traditional directed tests. Thus, these assertions and methods can now be applied to all the specification errors for the design. Let's look at some other complex specification error scenarios we had to validate. The below table lists out some of the challenging errors to validate using constraint-based random verification. Unbalanced Huffman tree. Compression algorithms may leverage Huffman encoding derived from balanced Huffman tree to further encode headers and payloads to improve compression ratios. In addition, the Huffman tree depths may vary within and across various compression algorithms. Decoding of incomplete or unbalanced tree and compressed payload translates to data corruption and must be detected and flagged by lossless hardware decompression IP as a specification error. This significantly increases challenges for CVRV methodology as a verification engineer now must do bit-level manipulation in the compressed file to cover every possible scenario that can result in unbalanced or incomplete tree. Using FPV with the formal engines can automatically identify cases to exercise incomplete or unbalanced trees. The next error is receiving an incorrect code. If a Huffman code in the compressed stream does not match any encodings of the Huffman tree, then the compressed payload is considered corrupt and shall be reported as a specification error. Next one is distance out of range. This error can result if the copy location of a token either violates the maximum supported range of the spec or goes beyond the available history range. This also requires bit-level manipulation of the compressed files for many different distance locations versus history distance versus spec requirements to cover every possible scenario. The next error is the incomplete stream. The decompression IP may track the number of uncompressed and/or compressed bytes based on header information. If the uncompressed stream has been fully decoded and the uncompressed bytes do not match the encoded value in the header, or the stream has been exhausted and the compressed bytes do not match, then the compressed block is considered corrupt. The last error we're going to talk about today is padding byte errors. In some cases, encoded padding bytes are required per the spec, and any corrupt padding bytes must be detected. Padding bytes can be in multiple places within the payload and at different FSM states of the design. Even though there is one defined error condition in code, it requires multiple corrupt compressed payloads with unique padding byte errors in different locations to fully validate. As you can see from these examples, the complexity in different combinations of errors is very challenging to get full coverage using CVRV due to multiple manual interventions with the compressed payloads. Now let's take a look at another FPV technique used for error handling verification. Another technique is the backpropagation of design constraints. In the event a counterexample is a result of illegal behavior, the design might need to be constrained. In the FPV environment, simple constraints, as seen here, can be placed deep within the design to provide only the cases that we want to see, and these constraints will backpropagate to the input. With this method, the formal engines will do all the heavy lifting at the interface to generate the correct input vectors that fall within the internal design constraints. That same constraint on the packet stream interface would be more complex and difficult to define. In this example, the assumption placed at the output of the packet processor will backpropagate to the input packet stream. This guarantees that the packet stream will only generate a combination of vectors at the output of the packet processor that adhere to the packet type assumption. Likewise, the formal engines will guarantee that the packet handling logic will only see input vectors that adhere to the same assumption. The use of backpropagation can be placed anywhere in the design and can be used across different design IPs. As with any constraint, it's important to ensure the intent of the constraint is not over-constraining your design and masking a potential issue. The next step of error handling verification is error reporting. The goal is to verify the correct error code and error code valid is reported out for a given error condition. Let's compare CVRV versus FPV methods for error reporting. In this example, error condition N represents detected error condition and error code N represents the expected error code for error condition n. Lastly, n represents the total number of error codes your design supports. In CBRV, the number of required test cases is equal to the number of supported error codes, 255 in our test case. CBRV requires generating error test vectors for each error code, or using an internal force methodology to trigger the error, both of which are tedious, complex, and time-consuming tasks. In FPV, only 2 assertions are required for each error code. While that can equate to many assertions, the significant difference is not needing to manually generate the test vectors to trigger these errors. With the 2 assertions seen here, the formal engines will generate any combination of only that error condition and check the corresponding error code matches the specification. The other huge advantage is the ability to do negative testing for all the error codes as seen in the second assertion. This guarantees that the unique error code can only be reported out for that error scenario. While we may not be directly using SVA assumptions and constraints in this example, the left-hand side, or precondition, for the assertions is treated as a constraint for that particular assertion and will backpropagate to the inputs. The use of free nets and backpropagation of constraints eliminate the need for multiple manually created directed tests and compressed files used in traditional CBRV methods. The last requirement for error handling verification, and one of the most challenging to get full coverage for sign-off, is graceful completion. So what is graceful completion? After processing any request successfully or unsuccessfully due to an error, the system shall gracefully exit to a known state and be serviceable for the next request. This requirement is extremely important because it is a key reliability aspect for network accelerators and ASICs alike. Any bugs in the design that prevent graceful completion can lead to a denial of service attack, which could allow an attacker with a bad compressed stream to put the entire system in an unrecoverable state, rendering it unavailable to the rest of the network. To help validate graceful completion, the last technique, and one of the more powerful ones, is inserting cut points into the design. This allows us to convert any internal signal in the design to a free random net. This abstraction technique allows the formal engines to randomize the behavior of this net without the need for the error condition to be produced from the compressed data stream. It accelerates modeling the asynchronous behavior of errors with respect to the state of the design because it doesn't rely on the design implementation to generate the errors. In this example, we will represent the control logic as our IPFSM and show how a cut point on the error signal helps validate graceful completion. Without the cut point, the compressed data stream input must go through the decode logic and the error detection logic to generate an error into the control logic FSM. Depending on the design complexity, this may cause convergence issues to generate an error in a deeper FSM state. With the cut point on the error signal, parts of the decode logic and all of the error detection logic, which has been formally validated already in the detection and reporting stages, can safely be abstracted out. Now the formal tool can easily assert the error signal in any state and any cycle of the FSM. This ensures all possible combinations of state versus error is checked to ensure the FSM will always reach and remain in idle in an error scenario. In our case, graceful completion was defined as the control FSM reaching idle state for any error condition so it will be serviceable for the next job. In CBRV, not only do we need to generate the error condition, the error signal also needs to be asserted in each state of the FSM. This can be challenging because some errors are only capable of happening in a particular FSM state. Therefore, multiple tests for different error codes happening at different states are required. Lastly, to sign off, thorough and iterative coverage implementation and analysis needs to be completed to verify all possible cases are covered. If there are any gaps, more tests and/or randomization is required. In FPV, you define the cut point on the error signal to make it a free random net. Then, only 2 assertions would be required to check all possible cases for error-related graceful completion sign-off. Formal coverage analysis is still needed for sign-off, but if the properties converge, you have high confidence your design will not have any bugs and will always gracefully complete when an error occurs. Now let's go through some real-world results. Like many other companies, we began our validation approach with traditional constraint-based random verification, but we quickly saw the challenges ahead to validate all the error scenarios within the schedule and resources. Therefore, we shifted our validation strategy to use FPV while also keeping the CBRV method in parallel. Due to this shift, we started FPV 1 quarter after our CBRV validation started. Despite the late deployment of FPV, we had a very high return on investment using this methodology. We were able to find 75% of the error-related bugs using FPV versus 25% for CBRV. We also did complexity analysis of the bugs identified using FPV and found that most of these bugs were complex and required multiple events to align correctly, which would have been difficult to achieve using the CBRV methodology within our schedule and resources. In contrast, FPV could have found all the CBRV bugs if FPV was deployed earlier in the design cycle. For completeness, the team reproduced all of the bugs in FPV that were found using CBRV. Due to this methodology, we were able to achieve our error handling verification goals 4 times faster than CBRV. The chart is normalized to 1 engineer's worth of work to achieve full sign-off for error handling and clearly reflects the challenges associated with CBRV, such as complex test bench development and directed focus tests to exercise specific scenarios. We leveraged industry standard FPV techniques to address bounded proofs and design complexity and achieve 100% convergence for all assertions. The team also used various formal functional and code coverage metrics along with iterative reviews of FPV test plans to sign off on our error handling verification for the lossless hardware decompression IP. In this presentation, we discussed the importance of error handling verification and its challenges associated with constraint-based random verification methodology. Based on the lossless hardware decompression IP, we demonstrated the effectiveness of applying FPV to error handling verification. We strongly believe that this methodology will also provide similar schedule savings without increasing project budget for a wide variety of designs, especially those which involve industry standard protocols and interfaces such as PCIe and AMBA. Some of the future work within our group includes leveraging these FPV methodologies in security verification for denial of service attacks. Thank you very much for attending our presentation. Does anyone have any questions?
So, if anybody has questions, as we said, it would be good to post and write inside the chat windows. I see there is one question. Could you, Bhushan and Peter, could you elaborate how to avoid over constraints at top level when reusing lower level constraints? For example, some lower level block boundary constraints may become part of the DUT internal interface at top level. So keeping those as constraints at higher FPV levels may be risky. Or do you convert those lower level constraints to checkers at top level?
I can take this one. So the answer is it's more the assume guarantee methodology, where you have the lower level constraints or the assumption that you have put in that converts as a checker for your higher level. So it's more like an assertion when you go at the high level, and then you build from bottom up approach.
Okay, thank you. I have a question. So were there any escapes from formal? And if there were escapes, how did you address them?
Yeah, I'll take that one. So we did have one escape that showed up in CBRB, and the escape was actually due to some gray areas within the specification. So it was also found using some extensive fuzz testing methodology that after we had already signed off on the design. So we did go back and reevaluate our code coverage, and everything was in place. What happened was this particular area was an error code that we had fully validated, but it had one level of permutation that was part of this spec misunderstanding that we didn't validate or wasn't part of our FPV plan. And so we went back and revalidated with FPV, and to address these going forward, it's really iterative FPV test plan reviews and making sure going through the specification versus our test plan to make sure there's no gaps within there.
Thank you. There is one more question in the chat. How do you take care of initialization sequence in FPV? As an example, to check error traffic cases for PCIe, successful link up and configuration required. How Formal takes care of this sequence?
So for this is more like think in terms of how your design is indicating that it is ready to or the successful link is set up, right? For an example, in the presentation, the third technique, that is the stop it, where you can create a signal as a free net, right? Same way within your design, you must have some signal indicating that initialization or the link setup is completed. And you can probably put a stop it and add assumption or abstraction behavior indicating that now the link setup is ready, and then you can move on to the next of the remaining verification. So that's one way of doing it. There are other abstraction techniques as well, where you can feed your sequences or the reset sequence, you can define it, or you can even use the waveform generated data and then feed it back to the formal tool, and then make sure that you already reach to the point where your reset or the other common sequences are already implemented, and then you are moving more towards the interesting scenarios.
Thank you. There is one more question in the chat. What was the equivalent input in your formal environment? Was it still the compressed data stream input? It is compressed data stream input treated as free nets.
Yeah, Neha, do you want to take that one?
Yes, I can take that. So because the input is treated as free nets, so we get the compressed data as the input. So our formal environment exercised all the bits that came in as input, which represented the compressed data. So to answer to your question, yes, it was the compressed data stream that was treated as the input on the free nets.
Thank you very much. And with this, we want to thank the presenters and the authors, and we will get ready for the next paper. The second
Awesome.
paper
Thank
is
you, everyone.
titled, thank you. The second paper is titled, How to Avoid the Pitfalls of Mixing Formal and Simulation Coverage. We have three presenters. Mark Eslinger is a product engineer in the IC Verification Systems Division of Siemens CDA, where he specializes in assertion-based methods and formal verification. Mark has over 30 years of experience in design and verification, applications engineering, and technical marketing. Joe Hupcey is a part of Siemens CDA product management team for design and verification technologies based in Siemens office in Silicon Valley. He is responsible for the formal product line of automated applications and advanced property checking. Prior to joining Siemens, Joe has held product management and marketing roles in several electronic design automation companies for products that covered multiple aspects of hardware and software functional verification. Before transitioning into marketing, Joe worked as an electrical engineer in FPGA design, EDA tools for FPGAs and ASICs, and ASIC verification. Joe's educational background includes BSEE, MSEE, and MBA degrees from Cornell University in Ithaca, New York. Nicolae Tusinschi is product specialist design verification at OneSpin, a Siemens business. That's right, OneSpin is now a Siemens business. He joined the team in 2016 and developed an exhaustive knowledge of formal methods and best practices with formal verification tools before targeting his focus on the company's OneSpin 360 DVT solution. Nicolae holds an MSc degree in embedded computing systems from Technische Universität Kaiserslautern in Germany and University of Southampton. Let's now watch the pre-recorded presentation.
Welcome to this presentation on how to avoid the pitfalls of mixing formal and simulation coverage. My name is Mark Eslinger. I'd also like to introduce my co-authors, Joseph Hupcey and Nicolae Tusinschi. Joe will start things off.
Thanks, Mark. Hi, I'm Joe Hupcey, and allow me to ask you if you've heard the following from your manager. I want to see coverage data from all sources combined into a single report so we can see our progress at a glance. I bet everyone in this audience has heard this at least once, and it's a fair request. Clearly, the motivation here is to leverage the strengths of multiple verification strategies to ensure the device under test behaves as specified. And thus, the corresponding challenge is to properly compare and combine the results from each verification strategy to the verification plan. The most common request we see is to merge simulation and formal coverage. But unfortunately, the most common problems we see is that users aren't sure what formal coverage is telling them in the first place and how to properly merge the formal coverage results with their simulation coverage data. But before we address these problems, let's start with a quick recap of simulation coverage. With code coverage, you're measuring the percentage of RTL code that has been executed by your tests. When your tests are unable to traverse into branches of the RTL state space, we say the code is dead code or unreachable, and often this means there's a bug in the code. However, while dead code is usually bad, it says nothing about the DUT's conformance to the specification. This is where functional coverage comes in. Functional coverage is a metric of how much design functionality has been exercised as per your mapping of DUT features in the spec to an associated cover point in the RTL code to be exercised by your constrained random tests. Coverage points have certain conditions, ranges, defined transitions, or intersecting paths called crosses to fulfill before the results show 100% coverage from your simulations. Now, before I go into formal coverage, let me first briefly digress on the nature of formal analysis versus simulation by making an analogy to finding solutions to the quadratic equation. With a constrained random simulation approach, you're effectively plugging in numbers in the hope that you eventually satisfy the equation. But the formal approach is an algebraic computation of the solutions to the Boolean equation that the formal tool generates under the hood to represent your DUT. The key thing to realize here is that this equation does not include time as a variable. This means that solutions are valid for all time, and thus solutions from formal analysis are valid for all inputs and for all time. In a word, formal is exhaustive. With this in mind, let's define the most common types of formal coverage. First, there's reachability, which is made up of a sequence of input signals which can reach the coverage element. Next, there's observability, defined as all possible state space paths from a selected node to signals in an assertion. The structural cone of influence, or COI, is all logic from a specified node back to the primary inputs. Finally, mutation coverage is comprised of automatically inserted mutations in the DUT to deliberately try and cause an assertion to fail. So given the definitions of simulation and formal coverage that I've just outlined, let me review some of the most common pitfalls of trying to merge them together. The number one caveat, regardless of whether simulation, formal, or both is being employed, is that just because something is covered doesn't mean it's properly verified. In specific regard to simulation coverage, it's important to understand that simulation coverage only reflects specific forward paths that the simulation has traversed from the inputs through the state space for only a specific set of stimuli. And for formal, some types of formal coverage also reflect a forward traversal of the analysis starting from the inputs, but often the amount of logic covered is greater than simulation. Additionally, other types of formal coverage work backwards from an output. Finally, regarding code coverage, the code coverage from simulation usually represents end-to-end cluster or SoC level testing, while formal code coverage is typically run at the block level. With that, let me turn the floor back over to Mark to show you some specific examples to illustrate these issues.
Thanks, Joe. We'll take a look at a few examples that will show some of the differences between simulation code coverage and formal code coverage. Our first example is a simple design. It has a select input, which can take on these 4 values, and there's 3 outputs, A, B, and C. And based on the select input, each of the outputs can go active. And there's a requirement that once one of the outputs goes active, then the next cycle it will be inactive. So it's a pulse. And you can write a property. Here's a shorthand version. If the output is active, then the next cycle it's inactive. And for the purposes of this example, we will only check this output B. So the property is written for the output B. So simulation will take this high and then low, and then formal will analyze the property. Here you can see the results of the code coverage for simulation and formal. If you look at the design, the select is registered, and that registered value goes into a large case statement here, which is doing the assignments for the outputs. Those values are then run through some logic, which ensures that the output is only active for 1 clock cycle, and then there's a final output mux. And as you look at this, you'll see that the vectors start coming in on the inputs and will traverse through the logic, and anything it touches is going to be covered. It's somewhat of a forward traversal. The property we ran in simulation here, of course, passed. And the select inputs, we did not use the values of 1 or 3. We were only stimulating what would drive the output B in this case. But you can see a lot of stuff was covered that we weren't intending to hit. Anytime you go into a block, of course, you're going to cover every statement in there. If you look at the formal side, the property was proven, and you're looking at the output B because that's what the property was written for. It's going to pull in the logic that ensures it's 1 hot because we proved that property, and then some of the logic that was used to stimulate this. So you can think of forward as moving backward from the property, only using the logic that's required to prove the property. And so that's what's going to be covered. Everything else is not covered. Obviously, in both cases, you're going to write more properties to cover the rest of the design or run more vectors in the case of simulation to cover the other scenarios. But you can think of simulation when you're calculating coverage as moving from your inputs all the way to the outputs, and there's a lot of stuff that gets covered. Formal is working backward from the property and only covering logic that's required to prove the property. Our second example involves a state machine. The initial state is state 1, and you're just going to hang out in this state until you get the start signal, which moves you into state 2. Here you hang out, and if the select is 1, you move to state 3. If the select input is 2, you move to state 4. And then once in state 3 and state 4, you hang out there until the done signal happens, in which you move back to state 1. There's an output M out of this design that is driven by state 3 and state 4 through some logic. And so what we're going to do is run simulation and formal on this state machine and the logic around it. And there's a requirement that the output is mutex, so only one of the bits is active at a time. And we're going to run this property through simulation, just driving, in this case, the test bench that's run will just drive through this part of the state machine, so ignoring state 4. And in the case of the run, the property passes in simulation and was proven in formal. Here you can see the code coverage for both simulation on the left and formal on the right. This design has a counter in it, which just counts, and the done signal is tied in with the counter. Here's the state vector, and then the next state case statement. And then you can see the output, which is based off of the two states. Again, you see that a lot of the design is covered. State 4 of the FSM is not covered because there were no vectors that ran through that, but everything else on this design that's not related to state 4 is covered. And the property passes, it is mutex for what was analyzed. If you look on the formal side, actually the FSM doesn't even come into play here when you're proving that this output is mutex. This final output mux here, all the assignments to the output mout, formal analyzes that and can very quickly and easily determine that the output is indeed mutex. And it doesn't really matter what the state machine is doing in this case. And so you don't have any coverage there. Now, this is a very simple property, of course, and actually this requirement that this output be mutex could be extremely important. So you do want to write a property for it. You obviously will need to write a lot of other properties that involve functioning of the state machine. And typically you're wanting to do higher order requirements of how the state machine works when you're writing those requirements. There are trivial analysis that you can do on state machines using automated formal techniques. So checking for reachability or deadlock, those types of things. And the automated tools are great for that. When you're looking at property checking, then higher order requirements are typically the best way to go. And you would, of course, write more properties, checking more requirements, which would include more coverage here. This is just another quick example of formal only using or covering the logic that's needed to prove the property. Here you can see a very simple design. There's 3 inputs, and based on the encoding, that drives 3 registers. There's 3 outputs, A, B, and C. And again, the specification for these 3 outputs is that they are mutex, so only one could be active at a time. And maybe this code is in some block, which is in some chip, and you've been running chip level simulations, and you're looking at your code coverage, and things are looking great, but there's a coverage hole here. So that's not good. And you have to go through the process of writing more vectors to try and close that coverage hole. And then you might be thinking, well, man, that's difficult. I don't know what vectors to change to. Maybe I can use formal to help close this coverage. And so that's the question. Can formal be used to help close this coverage hole? Now, ideally, you're going to close coverage using the engine that you've been running with. But in this case, maybe the engineer is very clever. Let's see, I can write a property here that if I drive the input 1 to a 1, then that's going to imply my output is a 1. You know, that's pretty quick and dirty. Let's do that. And so I run that property on this module through formal, and look at that. It covers that logic. This is awesome. If I merge that with my simulation, now I'm at 100% coverage. This is exactly what I want. I'm done, right? Everything's good. Everything's green. Finished. Or am I? Well, proving this property technically did close your coverage hole in simulation. It's really just useless. It's a bogus closing of the simulation hole because this property doesn't test anything. It's testing a gate in your design. It's like testing an inverter with a property. It's not doing anything useful. It's not tied to your test plan. It's not tied to design requirements. It's not going to find any bugs. It's not going to improve your verification. A better way to go about doing this is to actually look at the requirements of your design. And if you remember, in this case, the outputs were mutex. And so you can write a property to check that. And then run that property and gather coverage for that property. And then this would be more useful for applying in this scenario. This new property that tests requirements, you can see is proven and has good coverage from the formal perspective. And then this coverage could be merged with simulation. Ideally, you want to maybe take a look at boundaries, instance boundaries, and As part of your test planning, you're assigning different modules or different blocks in your design to be fully verified with formal or have major function verified with formal. And then as part of your test plan, you're not capturing simulation coverage in these areas, and then you're merging formal and simulation together. And so that's the ideal scenario, is having simulation and formal integrated together as part of your test plan, and then it comes to merging the coverage together. You are looking at what was covered with formal and what was covered with simulation, and ideally closing coverage in each of those domains based on your test plan. Nicolae will now give you another example.
Let's look at this example where we get 100% coverage, but there is still a bug. After running the tests, we have simulation and formal reporting to us that everything is covered. You can see that everything is green in pictures on the simulation, the picture on the formal. But in order to see where the bug is, we need to recall what the specification is saying to us. Here we have two spec items. First, saying that the outputs are mutex based. So we need to check the out1 and out2 signal. And also that the FSM to only be in state 2 for no more than 3 cycles. Both simulation and formal are 100% green, so this is great news. But there is still a bug. We've seen that for this example, all the code is traversed. Everything is green and 100% green. But the functional behavior is incorrect. Let's recall the key requirement, saying that the FSM to only be in state 2 for no more than 3 cycles. How do we deal with this? First solution would be to have a forethought to manually write and include the following assertion. So the assertion says the following, that once the ST2 signal rose, meaning that we are in state 2, after no more than 3 cycles, we are getting out of state 2. This approach is very error prone, as we are usually missing important items to verify. Another approach that we can take is actually leverage the automated mutation coverage in order to detect these the missing relay test for key requirements. Let's see how using mutation coverage helps us to identify verification holes in our verification environment. After running mutation-based analysis, we get such a report that highlights the verification holes in red, and we can see that for the state 2, we see that we are missing the check that verifies the requirement from our specification. Also, in addition, we see that our verification environment is missing a test for the reset behavior. But let's see how, in fact, the mutation-based analysis is actually working. For that, we need to introduce two terms, control coverage and detection coverage. Control coverage is about exercising, so it's about activating the location. And detection coverage is about detecting the mutation or / modification that has happened. So how does the mutation happens for that specific location? Instead of assigning the value that is from the design, there is a free variable assignment, and the expectation is that at least one checker to identify or to catch, to be more precise, this specific mutation.
Thanks, Nicolae. Let's take a quick look at a summary of some of the differences between formal and simulation coverage. Formal coverage is based on the properties you have in your design, whereas simulation is based on the vectors that are run through the design. The vectors in simulation go from your inputs to your outputs, so it's very generous in the coverage that you're going to get from that. Whereas with formal, you're only looking at the logic that was used in the proof. The coverage with formal is based only on proofs. So if you have a firing on a property, that's not going to contribute to your coverage. Whereas with simulation, if you're running a certain test, you may cover logic that's not related to that test. Some examples of this are anytime you enter a block or block coverage in simulation, all the statements are automatically covered. Whereas with formal, some of the statements may not be covered. Formal uses a synthesized netlist, whereas simulation will run on the RTL and could have some test bench components as well. Formal also uses abstractions commonly, especially if you're trying to do assurance and get proofs, and this can impact coverage, whereas in simulation, no abstractions are being used. Assumptions are used quite a bit in formal, and these input constraints are needed to be verified to make sure that they are correct, to make sure that the proof is correct. And in the case of these input assumptions or constraints, reachability can be impacted both in the simulation side and on the formal side, potentially causing unreachable logic, which can be excluded. So the reachability analysis is applied on both sides to help close coverage. And on the simulation side, formal techniques are used. And in the case of Siemens, cover check is the formal product that's used to close coverage on the simulation side. As you begin working with both formal and simulation coverage, here are some recommendations that can help ensure your success. Ideally, you want to close code coverage in each domain separately. So each engine, simulation, or formal that's used, close the coverage in those domains as much as possible in that domain. The purpose of code coverage is to point to holes in your test bench, whether it's in simulation or formal. And so you're wanting to improve your test bench to ensure that you are more rigorous in the verification that you are doing. Ideally, if you have the resources in the formal domain, use both proof core and mutation coverage for more robust test benches. Highly recommended to include formal in your test planning, especially if you're using an assurance methodology, meaning you're going for proofs, you're proving requirements. As part of this test planning, you can assign different blocks to formal for verification and then other parts of the design to simulation. And then based on these boundaries, you're doing verification in each domain and closing coverage in that domain as completely as possible. It's also recommended to make sure you have peer reviews to make sure that there aren't any shortcuts being taken or the properties, for example, in formal are tied to your requirements. Know where your code coverage comes from. Is it coming from formal? Is it coming from simulation? As you're merging stuff together, this is important to know where the coverage came from, especially in your peer reviews. You want to make sure that you're reporting, whether it's in various GUI environments or HTML or text, that you know where the coverage came from, and then you can make proper choices about where to go next. Avoid writing trivial tests in simulation or properties in formal to try and get to that 100% number. This is where you have to go back to your test planning to make sure that's complete. Holes in your test bench are pointing to an incomplete or weak test plan and a weak test bench. When you're adding properties on the formal side, make sure the properties you add are tied to your test plan and are checking real requirements. That will ensure that the coverage that you generate is good and can be merged in with other verification management tools. To wrap things up, I'll turn things over to Joe.
Thank you, Mark and Nicolae, for all those examples and recommendations. To summarize our presentation today, it is possible to combine the strengths of simulation and formal to ensure that your DUT behaves as specified. And you do this by understanding how simulation and formal coverage metrics work in isolation and how they combine to provide a holistic picture of the progress and quality of your verification effort. Finally, mutation analysis coverage is a powerful tool to make sure 100% coverage doesn't fool you into missing bugs in your test bench. With that, are there any questions?
Thank you, Joe, Mark, and Nicolae, for a very good presentation. I'm looking at the chat. I don't see yet questions, or there's something coming in. But first, maybe I can ask the questions. Please explain more the difference in using formal code coverage and cover check.
Yeah, so cover check is a reachability analysis that's used to help close coverage in the simulation domain. So it's using formal techniques to check for reachability. If code's unreachable, then you can exclude it. So it's closing that turnaround time between whether you can hit it with simulation or not. And once you exclude it, you can save, in many cases, man-months of effort closing simulation coverage. Formal coverage, of course, you are in the domain of using property checking, and you're wanting to make sure that your property set is complete. There are very there's similarities there. As Joe mentioned, reachability is one of the components of formal coverage as well.
Thank you. Thank you, Mark. There is one question now in the chat. How to merge formal coverage under over constraints into simulation? Most of our formal benches have both over and under constraints. Do you have any suggestions on how to use formal to guide simulation? For example, can we automatically replay a trace generated by a formal tool inside the simulation tool so we can have a fast simulation hit and a single place to merge coverage?
Yes, there's a couple of questions in here. With over-constraining, of course, that can lead to reachability issues. This is one of the reasons to keep simulation coverage and formal coverage separated in your analysis so you can tell where it comes from. If you have something that's unreachable from an over-constrained condition, then it's going to be excluded, at least in the way we approach it. Generating test benches. So with formal, any counterexample that you generate, you can create a small little test bench there and run a simulation on it. This can be done in a number of tools, depending on the property, or if you're doing reachability analysis, for example. I would categorize that under a trivial type of hit. If you're running formal at a block level, you're just running the simulation at that block level to try and close coverage. So not typically something that's recommended, although it could be done. So it's kind of on the user on how they want to approach things. Again, this is where peer reviews can come in. If it's something that everyone thinks is legal, then proceed. If not, then you would have to take other steps.
Thank you. Thank you, Mark. There are two more questions in the chat. How big a design are you able to use this methodology for? Simulation usually targets designs that are much bigger than formal. When hitting convergence issues, what are your recommendations?
That may be slightly outside the coverage domain, but yeah, with formal, you could run on kind of any size design, really. It's just the bigger the design, the bigger the state space, the longer the runs are going to be, and the higher the chance of not converging. So you're going to start using abstraction techniques and those types of things. Depends on what you're trying to do. So yeah, I mean, the size of the design, it's just formal. Yeah, go ahead, Joe.
Earlier, one of those techniques was cited in the prior presentation on using cut points, right? Where you can focus the analysis on a very specific piece of logic, effectively by electronically isolating that logic. And as Mark mentioned, there's all sorts of different abstraction techniques that remove logic or areas of design that are really not relevant to the analysis you're doing, and or can be compressed. I'm using that word very loosely. So you can just get the heart of the analysis and not have to worry about the kind of ancillary logic, like, for example, abstracting a counter with a very simple state machine. So you can get the basic functionality going without tripping over some formal unfriendly thing. So we have a lot of things on Verification Academy for that. So by all means, follow up with us. There's a lot of great techniques that are pretty easy to apply.
And obviously, if you cut some logic out, you're not going to get coverage on that. So this is where you're going to be merging coverage from different properties, for example, to get the ultimate final coverage number.
Thank you. The next question is, if RTL didn't implement the no more than 3 cycles in stage 2 feature as well, can mutation coverage find this bug?
Well, I will take that one. So, yeah, mutation coverage actually works on the assertion on the formal test bench. So it needs the assertions to hold in order to run the mutation analysis. So if the RTL didn't implement that, then obviously the mutation coverage will not catch that.
Got it. Thank you. The next question is, can you please provide a reference code example libraries available to try out and exercise formal coverage and simulation coverage merge?
So we have some of that ships with the standard examples in the tool. You go down to the examples subdirectory if you're if you're a customer of ours, and we address some of this on Verification Academy as well.
The examples that were in the paper are, well, you could cut and paste those and run them. I mean, I think they're complete or fairly complete. You might need to use the module or have a module definition added, or you can email me. I could probably tar them up and send them to you. They're pretty simple, just to get some points across. The question on merging databases. Yeah, there's techniques for merging the database. We use the UCDB file, of course, and simulation is going to have coverage data in the UCDB, and formal is going to have coverage data in the UCDB, both for code coverage and properties and functional coverage for that matter. And once data is in the UCDB file, the merging becomes straightforward.
Thank you, Mark. One more question. From slide 20, keep code coverage data from each domain separate in the main coverage database. So how do you merge them? Or you default to test plan coverage?
I just answered that one. So yeah, within the QuestaSim environment, it's vcover merge is the command.
Okay.
Yeah, and there's another question embedded in that, and there are some customers that do want to, like, literally kind of union them together, and you can do that. And hopefully we've shown in this paper that that's kind of dangerous to do, is to just blindly union the coverage from one to the other. The tool supports that, and you can do that if you want to, but think twice about it. And that's the point, one of the points we wanted to make in the paper. And yes, there's always test plan coverage, right? That's kind of the place to start, right? And this kind of came up a little bit in the other presentation earlier, is start with the test plan and the specification, really think those through, what you're trying to actually verify, and make sure that your assertions in this case, and constraints are matched to those goals. I think there's a great kind of example in that bug escape in the previous paper, right? That kind of showed what can happen if there's a misunderstanding in the specification.
And when you're talking about formal test plan coverage, is really tied to your property results. And of course, you want that to be complete. The code coverage aspect of it is pointing to holes that you may have in your test plan that you may not have considered before. Same thing for mutation coverage.
Yeah, that's exactly what
in the
makes
UCDB
mutation
file
so important.
Right. So in your database, you want to keep the data separate, and then only start merging stuff together when you're doing your final reports, to answer that last question about merging. So in the database, the data is separated so you can view it individually. But then, of course, the manager is going to want to see that 100% number. So at that point, you would probably show the final merged, which is the combination of simulation, formal, emulation as well, if you're applying those techniques. Thanks, everyone. Great questions.
Thank you, Mark and Joe and Nicolae. Thank you very much. We will go next to the third presentation that we have in this session. It is titled A Hybrid Verification Solution to RISC-V Vector Extension. The authors are from Mediatek, Chenghuan Li, Yanhua Feng, and Liam Li. The presenter is Chenghuan Li. He works at Mediatek on RISC-V verification since 2016. Let's now watch the pre-recorded presentation.
Hello, everyone. Very glad to have this opportunity to share our hybrid verification solution to RISC-V vector extension. I'm Chenghuan from Mediatek Beijing. Our team focuses at RISC-V verification. Okay, let's start. Here is my agenda. Firstly, I will give the overview about our design and test bench. Second part, I will introduce our verification solution from the following three aspects. First is the instruction model auto-generation to catch up with RISC-V's SRC evolution and to satisfy MTK's self-extensions requirement. Second is exception verification. RISC-V with Hager requirement for instructions contextual reference. We will demonstrate our verification strategy for with exception verification. Third is formal application. Formal was applied in our verification flow to solve specific problems and issues. We will demonstrate the two applications in our flow: early stage design explanation and hazard verification. Last part is a summary. In this page, the left part is our design. Our design is a 20-stage pipeline in order superscalar processor with configurable L1 and L2 cache. RISC-V IMAFCBP standard extensions were implemented in the scatter core. RISC-V vector extension is implemented in the vector core. Our test bench is a UAM-based simulation environment, including instruction auto-generation flow, layered sequence, and co-simulation with C model. We have an auto-generation flow to handle instruction modeling. The layered sequence is used to create test scenarios, and C model to co-simulation as taker. For processors verification, the first program needed to solve is the instruction modeling. The program increases when it comes to the frequent ISA changes from both RISC-V evolution and MTK's customization. The second issue is that it is necessary for DV to know some RTL's implementation information in both stimulus and checkers. Instruction generator can be divided into offline and online one. The offline instruction generator generates all instructions before RTL simulation. The online instruction generator generates instructions during the simulation. That is to say, generate instruction at every fetch request. Google provides an excellent RISC-V instruction generator, which is available in GitHub. It is a UAM-based instruction generator environment, and it is well handled branch instructions and memory load store instructions. In our flow, we choose the offline way. We use a vector to decouple fetch protocol. Instruction generation is used to compose the fetch bundle data from one simple instruction and handle sequential and non-sequential fetch requests. Base sequence is used to define the test scenario, and the sequence can be overridden to extend the scenario. The instruction class is organized like the following picture. It contains one base class and hundreds of extended class. In our flow, instruction classes are generated per design spec. The input files consist of YAML spec and one template. The YAML file describes the implementation-related information, including each instruction's name, decode, hardware resource, issue rules, and the exception rules. The template files are contained the instructions group information. The output files contains all instruction class basis group information and the instruction levels coverage. Our instruction class is organized like the following picture. It contains one base class and hundreds of extended classes. The base class is manually maintained, in which defines the instruction's prototype. The extended class is YAML auto-generated, in which fulfill each instruction's implementation information. The second topic in this paper is exceptions verification to RISC-V vector extension. The biggest challenge is that RISC-V vector extension with higher requirement for instructions contextual reference. This is a snippet of RISC-V's typical usage. First set VTAC, then vector load memory, then vector ALU, then change VType, then store memory, so on and forth. In such a program sequence, the SEW and the LMUL in VType raise requirement for the instruction type upon the index of the following instructions. If not satisfied, then exception is raised. The left table enumerates the exception category in RVV. As known, plenty of exception rules need to be handled in RVV. The verification strategy we adopt to this issue is divide and conquer. We separate the exception verification from normal one. For exceptions verification, we traverse all possible exceptions to fully test the exceptions rules. This is achieved by the two-layer loop. The outer loop traverses all RVV's instruction, and the inner loop traverses each instruction's exceptions rule. The exceptions rule is leveraged from the YAML spec. For normal cases verification, we created a funeral sequence to generate legal instructions as much as possible. The first layer is to decide the instructions type based on current VType setting. The second layer is used to decide the operand index to avoid index overlap. The third layer is used to handle unaligned memory access and CSR instructions read-write access policy. In this way, we achieved the goal to fully verify the exception, all exception rules. The third topic is the formal application in our RV-based verification. As is known, formal is a powerful verification methodology, but it has its limitation. I will demonstrate our two formal applications. One is the early stage design explanation, and the other one is hazard verification. As Shakespeare said, there are 1,000 Hamlets in 1,000 people's eyes. In verification world, there also exists a similar case. Verification always starts with one design spec. Then designer starts the RTL implementation, and the verification engineer starts to create a test bench. In traditional flow, this misunderstanding of design spec is eliminated using simulation, but simulation iteration speed is low. In our flow, we introduced the formal property verification in early verification stage. It is easy to set up formal ENV, and the formal iteration speed is high. From our execution experience, in early verification stage, about 80% low-hanging design bugs can be detected using this method. So first design bug can be reported after 1 week after RTL's release. The second formal application is hazard verification to achieve better PPA, both inter and intra-IW and WAW and WAR data hazard need to be handled in our design. Store and data forward are two common technicals to handle data hazard. This table shows the relationship between implementation and the design intent. If design intent is stalled and implementation is stalled, it is right. If design intent is forward and implementation is forward, it is right. If design intent is stalled and implementation is forward, it is okay. If design intent is either stalled or forward, but implementation doesn't handle it, it is a function bug. If a design intent is forward, but implementation is stalled, it is a performance bug. For performance bugs, simulation failed to detect them without specific local checkers. For function bugs, simulation may fail to detect despite having huge regression suit accumulation. The method proposed in this paper is that performance bug is covered in formal and function bug is covered in both formal and simulation. This page shows the detailed method we adopt. Firstly, we create language property to assert typical instruction requirement. This property is designed to detect the deadlock or landlock cases, which is the first concern. Some function bugs are formed using this property. As known, the liveness property is hard to be fully proven. So, in the second stage, we redirect to ask a formal tool to find out the long stall cycle cases. In this stage, engineers need to involve to analysis this cover trace to judge each cover trace is reasonable or not. During this process, we found a few performance bugs. The purpose of this stage is try to find out the longest stall cycle. After we got the longest stall cycle, in the last stage, we can change the longest property to safety property. And safety property, we can get a high proven rate. Here is a function bug found using longest property. Instruction vnclip.qv cannot be returned forever. The program sequence encounter example is like this. The lookout is that the design didn't consider LMUL when handling IW store. vclip.qv is a double narrowing instruction. Only consider double narrowing, vclip.qv needed v0, v1, v2, and v3, total 4 registers. But consider LMUL fractional 4, vclip.qv only needed v0. So actually, the first instruction VLW and the second instruction vnclip.qv has no data dependency. But our RTL implementation didn't consider LMUL when handling this data hazard, resulting in unexpected IW stall. This IW stall lead to the vclip.qv, the unnecessary stall at E5 stage. And in such an instruction sequence, the second vnclip.qv cannot be returned forever. In the Leibniz property, Formal easily find out this counterexample. Here is a performance bug found using cover property. The lookout is an unexpected WAW stall. The instruction sequence is like this. First, VADD, second, VLW.V, third, VMAC. Expected register from in the view of register returns order, expected order is V8 from VLW, then V4 from VADD, then V8 from VMAC. Totally need 10 cycles. Actually, in RTL's implementation, the register return order is V4 from VADD, V8 from VLW, then V8 from VMAC. Totally need 14 cycles. In this case, there is no function issue. V8, V4, the register's value is has no function issue, but RTL's implementation spend 40% effort to achieve this goal. So this is a function bug. This page shows the result. Using the hybrid method, first RTL bug can be formed after 1 week's RTL predicts. Formal plays an important role in the early stage bug hunting. It can help shift left sign-off schedule with 2 months, and the design quality is better. The last part is a summary. In this paper, we demonstrated our YAML-based instruction model auto-generation flow, which responds well to RISC file evolution and customization changes. Our with exceptions are thoroughly verified with UVM-based solution. Verification schedule shift left with simulation and formal hybrid solution. And that's all. Thank you.
Thank you very much. Was very good presentation. I'm going to the chat window to see if there are any questions. Please type, post your questions in the chat window if you have questions for Chenghuan Li about this paper. Okay, if you think of more or any questions, please type them at any time and we will do our best to get those answered. We will go next to our next paper, paper number 4 in our session today. It's titled Innovative Uses of SystemVerilog Bind Statements with Formal Verification. The presenter is Feng. He is the leader of formal verification group at Samsung Austin R&D Center and San Jose Advanced Computing Lab. His team supports GPU projects within Samsung. He received a PhD degree in formal verification from University of British Columbia at Vancouver, Canada. Before joining Samsung, he led the formal verification efforts at Oracle Labs, NVIDIA, Freescale, and AMD. He has 6 verification patents and has published more than 30 technical papers. Let's now watch the pre-recorded presentation.
Hello, this is Xiushan Feng. I'm from Samsung. Today, I will present innovative uses of SystemVerilog bind statements within formal verification. This is a joint work with my coworker, Christopher Starr, at the Samsung Austin R&D Center. Here is the agenda for this talk. First, I will give some introduction for background, which includes SystemVerilog bind statement, the syntax and the usage, then followed by some basics of formal verification and how SystemVerilog assertions are used inside the formal verification. With this background is given, then I will present the use cases of bind statement within formal verification. These use cases are based on hundreds of test benches developed by my coworker and I within Samsung. These use cases will fall into 3 different categories, which include sequential checking for clock gating, data path verification, and the formal property verification. Let's start with the introduction of SystemVerilog bind statement. Here is the syntax. I copied it directly from SystemVerilog language reference manual. And this is the definition of a bind derivative. There are 2 uses of a bind statement. The first one, you can bind to a target scope. A target scope can be a module or interface, and with optional instance list for that target scope, followed by the bind instantiation. The second usage is you can bind to the target instance directly. And the bind instantiation can be a program module interface checker instantiation. And I have a diagram here show you the typical usage of a bind statement. A green box here is the target, and it can be a RTL module or interface. And the green box here is the verification code. We give name for full. Full can be a module program interface checker if target is a module. On the inside of full, we can define verification code, assertion, and then we bind to full to our target. And with the extension of the full. If target is an interface, then full must be an interface or checker. So this is the bind statement normally we use for verification code, also in formal verification. And we can see we can easily add verification code into RTL design, and such verification code is separate from RTL. And normally such verification code won't be part of RTL synthesis. Next background is a formal verification. For formal verification, what we're trying to do is we try to prove for all possible state of a model, which is a secretary for our case, given the assumption, the property P holds true all the time. And the assumption and the property are all written in assert or assume type of assertions. And we can safely call formal verification as assertion-based verification. You have to write a lot of assertion for assumption and for properties. And sometimes we found it's not easy to create assertion without some helper RTL logic. So we have to do a lot of RTL modeling to simplify writing some assertion. And it's also very convenient to add some actual logic. So it's easy to debug. We can looking for the trace and easily find the root cause. And also for such complicated helper RTL logic, we don't want to write it inside RTL design that can contaminate our RTL. So we want to make it separate. And come to the formal verification tool. There's a lot of features inside the formal verification tool, but what I want to focus here is most of the formal tools allow you to manipulate the design. One example I want to show here is a sleep driver. Sleep driver is a command from one of the formal verification tools. What it does is cutting the driver of a logic. So for example, here we have two logic cone. We have the left one driving the right side logic cone, and the full is a signal where we want to do a sleep driver. So after applying this sleep driver command on the signal full, we actually remove the driver. So now full become a floating net. And the previous driver of full now can be referred as a dollar driver full. So with full be cut out and being a floating net, which allow us to add in constraint, because in our formal verification tool, a floating net works same as a primary input. And then we can add any constraint. We can use any logic to drive in full. By doing this, we actually manipulate the design logic. Now let's come back SystemVerilog assertions. There are two types of SystemVerilog assertion. The first one we call the immediate assertion. The second one is a concurrent assertion. So immediate assertion, normally we check is a combinatorial logic. Expression we want to check here is the combo logic. And for concurrent assertion, we can do temporal logic. You can allow has a sequence, you can have implications. And for immediate assertion, there's no property keyword, there's no clock defined, and you don't need to define disable conditions. And the immediate assertion must be defined inside a procedure statement, such as always combo. So at least a table here that lists the difference between immediate assertion and the concurrent assertion. talk about the evaluation region, intention, location, but the key part is immediate assertion is working on combinatorial circuitry and it doesn't have any clock. And we're gonna use it for our use case later. But here's a simple example to show you how formal vacation combined with assertion on the bind statement. It is a very simple toy example. The green box here show you an RTL design. We have input, we have output, and the input is valid and data valid on the data. Then we have the ready come as output, tell our producer that I'm ready to receive the data. On the internal, we have FIFO, we have clock, we have push PAL, we have full empty flags. And what we want to check is for this FIFO. So we can create a module which we call assertion ABV, assertion-based verification checker, and as the port connect to design. It connect to the valid, connect to ready, connect the data, and anything else. And we can define the default clocking for our assertion, and we can model our local push. We can build an RTL logic for local push using primary input. Then we create our assertion and assumptions. In order to make formal vacation work, we have to tell the tool how that input is controlled. You cannot have any random input. For example, when the valid is true and the data ready is not set, then the data should be stable. So we have this valid, not ready. Valid need to be whole, and valid, not ready. We need to have data stable. And they want to check if we have the full condition, there's no push, and if it's empty, there's no pop. And we also want to do a cross check between the local push we built using the primary input, check against the internal push that built by the design. So we can create assertion, make sure they are equivalent. With the RTL design here, and with the checker module, then we have our bind statement. We bind this ABV checker module to the DUT module, and with the instantiation. So this is our assertion. It's outside the RTL separate file. We send our RTL file list and also assertion file list to our formal verification tool. The formal verification tool will compile the design, synthesis the RTL and together with the assertions, and using formal engine to prove whether the assertion are true or not. If assertions are true, we call it proven. If not, the tool tell us a counterexample. And sometimes the tool has inconclusive answer. The tool tell you within a certain number of cycles, the tool cannot find a counterexample, and the tool cannot guarantee beyond that cycle whether the tool can hit a counterexample or not. So that's the formal vacation result. At this point, we have complete the introduction of background and come to our use cases. Let's start with the first category, formal clock gating verification using sequential equivalent checking. Inside our clock gating design, we're using ICT cell, where the clock can be disabled or enabled, depends on the enable input. So for this IGT cell, we build our clock enable, rely on the subunit activity signal. If a subunit is active, need a clock enable, then we enable the clock gating, we will have active clock for them. And for safety reason, we create some chicken bit, can be a register control or primary input. If there's a bug after we tape out the chip, we can disable the clock gating. But normally we don't want to do that because that's gonna be for actual powers. So for security equivalent checking for clock gating, we actually play with that chicken bit, set the chicken bit be 1 and 0, and then using this sequential equivalent checking tool to prove we have equivalent output. For formal verification of clock gating, we always want to have a full proof or deep proof. But for most of the case, it's really hard to get a full proof at the unit level. So we have to do divide and conquer at the subunit level. So in this use case 1, show you a solution using bind statement, how to work at the subunit level clock gating formal-cation. Here's the circuitry. At the D level, D is a unit name. On the field hierarchy below D, we have module C. And the C is really hard for formal equivalent checking tool to prove the equivalency. We found a lot of flaws within C cannot be proven between the spec and input. So we need to build a test bench at the unit level C. But the challenging part is we don't have IGG cell within C. We only have clock enable, and we have gated clock as the input. So how we solve it? The solution is we can use a bind statement. We can bind this IGG cell to module C. The IGG is come from our RTL library. And this is the user name for this IGG cells, F3 IGG. And we're using that clock enable from the output of module C to driving this IGG cell. And we'll keep the output clock and the input always on clock floating, so we can use Tickle to control them. So at this few lines of Tickle, what we did is we tell SEQ2, the top module of this test bench is module C. And when we map the input output for module C, we don't want to map the G clock, which is the gated clock for our input instance. We want to have always on clock for our spec, and we want to have the gated clock enable for module, for instance, input. So for this case, we defined always clock for the spec and always on clock. Since this always on clock is undriven, then formal equivalent check tool will automatically map between spec and input. So the spec always on clock, input always on clock is always on clock. Spec, the gated clock is also always on clock. Then our input gated clock is controlled by this output of IGG cell. So by doing this, we can create a test bench and verify at the module level C. Once module level C has been proven be equivalent, and we prove the implementation of clock enable is correct, then we will move to module A or module D. We can black box this module C, or we can using always on clock directly driving module C. That can significantly simplify the verification problem. And one benefit for this approach is when we're building test bench for module C, we don't rely on the implementation of D. We don't need D to complete that IGG implementation. If D is waiting for some other signal from different module, we need to wait that. As soon as the module clock enable was defined for module C, we can start to verify, and that's one of the benefits. The second use case of clock gating formulation using bind statement is how we use it to apply temporal RTL fix. Sometimes one formal run can find multiple RTL bugs, and we got the bug fix from the RTL designer, and we need to verify them one by one. And sometimes we don't want to hack our local RTL build system, and we don't want to recompile our bench for each of the fix. So here's an example. We have an RTL module, and we found a bug. RTL designer suggests us, oh, there's an extra term missing for that clock enable, and could you add it and test it? So our solution, instead of hack this RTL file, we create a checker module outside RTL, and we call it F3 full module. And we build this correct logic for the fixed RTL for clock enable. Then bind to this checker module to the design, and we call it instant full fix. On the inside of our Tickle control file, what we're gonna do is we will tell the tool do a sleep driver. So we will sleep driver for this full instance, the design module clock enable. We do a sleep driver, remove the driver, and we use SEQ map. That means we will do the same for input as well, and let the tool to map it because it's undriven. So the tool will automatically map it. And for this design, we create a session. We want to check the driver because anytime we do a sleep driver, we map them, the assumptions that they have the same driver. So we need to verify they do have a same equivalent driver. And then we will make assumption. So this is a bug fix come from our input, from our full clock enable. So we using the input design, tell the tool, here's the fixed RTL, let the current input instance pick up the fix and apply to it. So 3 lines of Tickle, we apply this RTL fix without touching RTL. Just like I mentioned at the beginning, we can use a sleep driver and assumption to manipulate the design. So our design using different driver. And if after we verify this, we verify, yes, this full fix, it works, and then we can disable it. very easy to disable from the GUI or command line from the VC Form tool. For example, we tell the tool, please remove this sleep driver, and then please remove the assertion, and then remove the assumption. So we can apply, move to the next RTL fix without actually reloading, recompile the RTL, without need to hack the RTL file. The first two use cases are for clock gating and CQ. The next two use cases are for DPV, we call the data path verification, or C2RTL equivalent checking. The C2RTL equivalent checking became very popular for our GPU and CPU design with recent machine learning related instruction added to the design. And we need to verify the equivalency between two different models. We call the spec input. Spec can be written in C or C++. Input is written in RTL. And our goal is to prove the transaction level equivalency. We need to map the input output. We also want to have full proof. So the challenging part for this work is how we map the IOs and how we receive full proof. Remember, we are working on a product state machine. Our state space double with the spec input. The first use case of DPV is how we constrain the input. Just like I mentioned, mapping the input output can be very challenging because the C and RTL need to have bit accuracy mapping, and sometimes they are not available. And for typical control file, we need to access some text macro to allow us to have parameterized the mapping on different config. Typical file cannot read our text macro directly from the C compile environment. And if we write helper RTL logic, that can simplify the problem. So for example, I have an example here is we have a C model. For C model, we try to compute the color blender. We call the color blending, work on 4 pixel 2x2. And then we have multiple source input. So the source input data 1 can have 4 pixels. And then using the integer data type from the C model, which is 32-bit, and has only one color format, is the RGBA. And in the RTL, we're using 38-bit for the input data 2x2. We have 4 pixels here. And we also have color format, which define different format other than RGBA. We can have ARGB, whatever other format. And then if we need to just control using a typical control file to mapping the IO, the problem becomes very complicated. Also, this color blender, the state space is pretty big. In order to have full proof, we have to do some, we call the case splitting on different case. And we have to do some case splitting. And we need a certain way to allow us to easily do that. So the solution we have here is create a helper logic module and then bind to the design. So we have this color blender RTL module. We create an RTL file, and then we can read all this color blender parameters from the RTL environment. We're building our helper logic. We're building a new data format. This new data format is a 32-bit for each pixel. And we assemble the input based on different color format. And we also detect whether data is valid or not for each pixel. So we're building helper logic within our map-based module. Then we start our mapping. Because our map-based, we create this new data. And the new data is mapping to our RTL for the color format. We do the conversion within this helper module. So our C model, the source data, the first cycle, we call the phase 1, can be mapped to our RTL, which is our map bit that's instant SR0. The new data has a 30-bit mapped to, for each pixel, mapped to our C model. And then we can also tell the tool, you need to have valid input from the RTL. So we make assumption, the in-data valid, which we created based on different format, we need to make sure our input is valid. So make this two assumption, then we can map the IO, and we can also constrain the input. Then we can do case splitting, depends on different format based on the helper logic signal. Then doing this, we can map the IO between the C model and RTL, and then we can do case splitting, and eventually we have the full proof. The second example of a DPV is how we're using a bind statement to verify a decompressor. We have a compressor and a decompressor. They locate a different cluster. There's no direct input-output connection between them. We already verified the compressor using the C2RTL, and we cannot using C2RTL to verify the decompressor because the C model is too complicated for Formal 2 to handle. So our approach is we do a couple or sleep driver within the decompressor, and we found the internal signal within the compressor which has the compressed data, and directly use it to feed the couple. So here's our solution. First, we're using bind statement. We bind our decompressor to the compressor module. Then all the signal within decompressor can be visible to the compressor. So now we do a couple for the decompressor instance, where we find the input for the decompressor kernel. Then we using the compressor internal signal, the output of the compressed data directly drive the internal signal. So by doing this, we can verify whether the input primitive is equivalent to output primitive after a certain cycle of decompression. Our last two use cases are for formal prompt verification. One is how we using bind statement to write a concurrent assertion for a combination module. Also, how we using bind statement to handle parameterized RTL. So here's a concurrent assertion for combinational module. If you have combinational circuitry, you want to write assertion, you want to write a concurrent assertion, then you need a clock and a reset. Also, Formal 2 always prefer concurrent assertion. So how we handle that? So we create a checker module for that DUT, which is a combinational circuitry, and we bind that DUT with a F3 checker. We define clock reset, but keep them floating. If we move to a different hierarchy on top of DUT, we're using real clock and real reset. For example, full is one level higher than DUT. We can use the real clock from full and for reset clock. And when we're doing our tickle, we define this top DUT when we work at the DUT level. Then we create a clock reset using this 14.9, we drive them. And we can write a concurrent assertion inside F3 checker. And this F3 checker file works with within DUT or any hierarchy about DUT, and we don't need to change it. The next one is how we handle parameterized RTL. This is an example from our ECC checking. We have 10 plus configurations for ECC inside our project, and we need to verify each configuration. But we don't want to have separate checker file, separate tickle file. So the approach is we're using a parameterized checker module. We bind to the parameterized checker module to the RTL with the parameter from RTL file. And then when we're using our tickle control file, we read the parameter from Unix environment. So we're using the environment variable, and we're using the p-value inside the combination of the RTL compile file. So when we're doing this compile, we can override it. So for example, in our shell script, we can override the environment variable, we can pass them to the script, then we can handle all of them with a multiple run. We don't need to touch tickle file, we don't need to change our checker file. So this is very convenient for future maintenance. Now come to the conclusion. From this talk, we can see formal verification is assertion-based verification. Helper logic assertion are heavily used. Together with the tickle controls, bind statements become very powerful in formal verification. There are 6 use cases are given in this talk. We can see any innovative use of this bind statement can greatly simplify the test bench on the future maintenance. We can also verify clock gating even before RTL is complete. We can use bind statement to help formal convergence. And now I'm ready to take a few questions.
Yes, thank you, Sean. Please, everyone, if you have questions, please type in the chat window box. Or if you prefer to unmute and just ask the question, that's fine also. Okay. If there are no questions, thank you very much.
Oh, there's one question.
There is one, yes. Can you help comment on the clock gating logic size used in binding methods to sign off?
Okay. For clock gating, it's a very big question. Based on my personal experience, at the beginning of the project, we only have about 10% of our test bench we can have foolproof, and we are working at we call it unit level. So, for example, for our GPU, we have 7 clusters, and we have about 40 units. And among these 40 units, we create about 100 test bench. And we have around, I would call it the first beginning, and we have about 5 to 6 units have foolproof. But we push pretty hard for this divide conquer approach. We have which apply many other advanced technology, and now we achieve about 30%. So the size of the design can be very big. We can have like a say like 100,000 flop size, and one unit we can have 30 or 40 clock domain. The design can be very complicated, and we have we call it a rigid rule to define when to solve, how to solve. So our bug miss rate is pretty low. In the past one project, I don't think we miss any bug after formal complete. Does that answer the question?
Yes, thank you. Yes. Yeah, please type if you have questions, or if you want to unmute, that's fine also. If no more questions, I want to thank all the presenters in our session today, and everybody please join me and let's put our thanks together to thank the presenters once again. On behalf of DVCon, I would like to thank you all in the audience for participating in this event, and we hope to see you next year, preferably in person. And one more time to remind everyone to submit your ratings for best paper presentation. There is the voting button, so please submit. With this, thank you again for this great session. Goodbye.